Good morning, good afternoon, good evening, everybody, and welcome to implementing IPv4 Multicast Routing. My name is Brian McGann. I am a CCIE in Routing and Switching, Security Service Provider, and Data Center, as well as a CCDE in Design. For any questions that you guys have after this course, you can email me at bmcgann@ini.com, follow me on Twitter at Brian McGann, or on linkedin.com/in/bmcgann. Now, in today's sessions, we're not going to be going through slides. We're going to be spending most of the time on the command line. And what we're going to be doing is building a multicast network and then going through some packet captures to see what's going on behind the scenes and talking about the specific configurations, the specific verifications of how a multicast network is functional. Okay, so the first thing that we need to do, and let me go ahead and make a list of the tasks that we need to accomplish here. First thing we need to do is to define our underlay unicast routing. Okay, the reason why we need unicast routing is that Protocol Independent Multicast is an independent protocol. It doesn't exchange its own topology information. So we need unicast routing in order to provide the loop-free tree in order to build multicast. Okay, next step is that we're going to enable multicast routing. Okay, with the IP multicast routing command. Next step is we're going to enable PIM at the link level. And then the next step is that we're going to test the multicast trees. Okay, and most of our time today is going to be spent on step number 4, where we're testing the multicast trees and looking at specifically what the details are of PIM, of how it's building the multicast tree from the sender to the receiver. Okay, for our underlay unicast routing, we're going to be running EHRP here. So it's going to be just a simple configuration that I'm going to be doing on all the routers at the same time. So we're going to go to global config. We're going to go to router EHRP1. We're going to issue a network statement for the transit interfaces, which are 155.1.0.0, and then also the loop backspace, which is 150.1.0.0. Okay, next step, we're going to look at the show IP EHRP neighbors and make sure that we have EHRP adjacencies on all of the devices. And it looks like this is good so far. Okay, now when we enable PIM, we want to enable PIM on a one-to-one basis with the unicast routing. So essentially all of these interfaces here that we're running unicast routing on, these are the interfaces that we're going to be running PIM. So in global configuration, we're going to say IP multicast routing. And then we're going to go to the physical interfaces, or in this case, the sub interfaces, and enable PIM in sparse mode. So we're going to start with the loopback interface. Okay, the loopback interface does need to run PIM for certain functions, which we're going to talk about in more details later. So we say IP PIM sparse mode. Okay, then we're going to enable PIM on all of our physical interfaces. So all of the interfaces that are running EHRP adjacencies, we have IP PIM sparse mode. Okay, same thing on router 2. So on interface loopback 0, IP PIM sparse. On interface gig 01.23, IP PIM sparse. And on tunnel 0, IP PIM sparse mode. Okay, same thing on router 3 here on interface loopback 0, IP PIM sparse. On gig 0/1.23, IP PIM sparse. Gig 0/1.13. Gig 0/1.37. And then on interface tunnel 0. Okay, same thing on router 4 here. So on loopback 0, IPPIM sparse. On gig 0/1.45, IPPIM sparse. On interface tunnel 0, on gig 0/1.146. Okay, on router 5, on our loopback 0, IPPIM sparse. On interface tunnel 0, IPPIM sparse. On gig 0/1.58 and gig 0/1.45. Okay, so these are all the same interfaces that are running the EIGRP process that we're just enabling the PIM process on. Okay, so interface loopback 0, IPPIM sparse. Interface gig 0/1.146, IPPIM sparse. Gig 0/1.67, IPPIM sparse. Okay, likewise on router 7, interface loopback 0, IPPIM sparse. Gig 0/1.79, IPPIM sparse. Gig 0/1.67. And gig 0/1.37. Okay, on router 8, we have the loopback, IPPIM sparse. Gig 0/158, IPPIM sparse. Gig 0/1.108, IPPIM sparse. And then on router 9, loopback 0, IPPIM sparse. And on gig 0/1.79, IPPIM sparse. And then lastly on router 10. Okay, loopback 0, IPPIM sparse. And gig 0/1.108, IPPIM sparse. Okay, so if we look at now the difference between the show IP EIGRP neighbors and show IP PIM neighbors, we should see that basically these are on a one-to-one basis. Show IP EIGRP neighbors and show IP PIM neighbors. Okay, so on router 1, we have router 4, 6, 3, and 5. We have 4, 6, 3, and 5. Okay, on router 2, we have adjacencies on gig 0/1.23 and on the tunnel interface. On router 3, we have the 3 gig interfaces plus the tunnel. And I'm just going to go here through these quickly and double check that we have adjacencies to all of the other neighbors. Okay, if we run into a problem where we don't run PIM on the interface that's running IGP, this is when we can run into a reverse path forwarding failure, or it basically means that the multicast traffic can be dropped when it's received inbound when it checks against the topology table. Okay, so PIM is running now on all of the interfaces plus the DMVPN tunnel. And the next step is that we need to define a rendezvous point that we're going to be using as a central collection point for the senders and the receivers. Okay, so in this particular case, we're going to use router 2 as the rendezvous point. And there's a couple different ways that we could assign router 2 as the rendezvous point. We could go to each router statically, and we could use the IPPIM RP address command and statically define router 2's loopback as the rendezvous point. We could also use 2 dynamic mechanisms, which are either AutoRP or BSR. In this particular case, I'm going to use Bootstrap Router because it's fairly simple in order to advertise the rendezvous point through BSR, because we're already running PIM adjacencies between all of the different devices. Okay, so on router 2, we're going to go to global config, and we're going to say IPPIM RP candidate, and we're going to advertise our loopback 0 as the RP candidate, and IPPIM BSR candidate likewise as the loopback 0. Okay, we should now see a log message that we have a tunnel interface that comes up. The tunnel interface is going to be the register tunnel that we're using to get to the rendezvous point. Okay, so everyone has line protocol 1, tunnel 1 coming up, which means that they are learning about the rendezvous point. Okay, to verify this though, we're going to look at the show IPPIM RP mapping. And we should see that router 2's loopback 150.1.2.2 is mapped to all multicast groups 224.0.0.0/4. So unless everyone in the topology agrees on the rendezvous point, we're not going to be able to process the join messages and the register messages properly in order to actually build the multicast tree. Okay, so everybody agrees that router 2 is the rendezvous point. Okay, so the next thing that we're going to do, we enabled our multicast, or we enabled our underlay unicast routing, so we're running EHRP. We enabled multicast routing on global config. We enabled PIM at the link level. Okay, actually there should be 3A here, which is to define the rendezvous point address. Okay, and now we can test the multicast trees. Okay, so we're going to use router 9 as a sender, and we're going to use router 10 as the receiver. Okay, so let's go ahead and do some packet captures on the back end. And we're going to look at the specific messages that PIM is generating when we go to send multicast traffic and when we go to receive multicast traffic. So let me open up my viral box, and we're going to go to the interface for router 9 gig 00, and we're going to do a traffic capture. Okay, and also we're going to do a traffic capture on router 7. Router 7's gig 00. Okay, so we should have 2 captures running, one for router 7, one for router 9. And we're now going to go to router 9 and we're going to ping to a multicast destination. In order to test the register process. Okay, on router 7, we're going to look at the debug IPPIM. And the same on router 2, which is the rendezvous point, we're going to look at the debug IPPIM. Okay, what we should see happen is that when we ping the multicast group, PIM is going to generate a register message, which is a unicast message between the designated router and the rendezvous point, telling the rendezvous point about the source and the group pair that we are sending the traffic to. So we're going to do an extended ping here. Target address will say 224.999, so any multicast group. Okay, we'll send 10 packets. Extended commands yes. Interface is going to be out loopback 0. Source is going to be 150.1.9.9, which is the loopback interface. Okay, now we don't have any receivers yet, so we're not going to receive any traffic back in. We're not going to receive an ICMP echo reply back in. But what we should see is that we generate a register message talking about this, the source and group pair. Okay, so on the rendezvous point, we received a message that says send register stop to 155.1.79.9 for group 150.1.9.9, group 224.999. So if we look at on all of the devices in the middle, and we look at the show IPM route for 224.999, we should see that the rendezvous point knows about both the star comma G entry and that it knows about the S comma G entry. Okay, if we look at the other devices in the middle, they're not going to know about these groups yet. Okay, router 9 should know about its own sending address, 150.1.9.9. But router 7 likewise does not know about this. So let's go ahead and look at our packet capture on router 9. And let's sort for PIM messages. Okay, so we see the PIM hellos going to the multicast group 224.0013, which is the well-known multicast group for PIM. We also see the bootstrap messages. That is going to be router 2 advertising itself as the bootstrap router. So under the PIM options, it says the BSR and the rendezvous point is 150.1.2.2, and it's servicing groups 224.000/4, which is the entire multicast range. Okay, what I'm looking for here, though, excuse me, what I'm looking for here is the PIM register message, which is going to be when we are pinging, and this might be under ICMP. No, let's check router 7's capture. Okay, let's look for PIM. And we're looking for a unicast message that's going from router 9 to the rendezvous point. Okay, it might be encoded inside the ICMP. Okay, let's try this again. Let's go to router 2, who is the rendezvous point, and let's go ahead and capture on router 2. Oh, and you know what? Actually, I was capturing on the wrong interface, is what it was. So let me trash these two captures. And let's go to router 9, gig 01. Okay, and router 7, gig 01. Okay, so let's ping to a new group. So on router 9, we're going to look at the debug IP PIM. And we're going to do an extended ping again. We're going to ping to 229.99.99.99. Extended commands, yes. Interface is going to be out loopback 0. And source is 150.1.9.9. Okay, so the first thing that the router is doing is checking to see who is the rendezvous point for this particular group. It says we found the rendezvous point. We checked the rendezvous point 150.1.2.2 against the group 229.99.99.99. We're now sending, adding a register and cap tunnel forwarding interface of 150.1.9.9 to 229.99.99.99. So this is going to be our unicast message to the rendezvous point, telling it that there is a sender 150.1.9.9 that's sending to group 229.99.99.99. We then get the acknowledgement back in, which is the register stop from the rendezvous point. This means that the rendezvous point is successfully accepts this message and it installs it in the multicast routing table. So if we look at router 9 in show IPM route for 229.99.99.99, we should see we know about the star comma G entry and the S comma G entry, the 150.1.9.9 going to 229.99.99.99. And if we look at router 2 and look at the same thing, show IPM route, we see star comma 229.99.99.99, and we see the specific source. Okay, now currently the outgoing interface list is null. This means that we know about the sender, but we don't know about any of the receivers. Okay, which is the normal point at this stage, because we haven't done an IGMP join message in order to actually accept the multicast group traffic on the other end of the link. Okay, so let's go back to our packet captures. And let's look at the capture of router 9 and look for PIM. And now we see the unicast message. Okay, so the registration message is going to be the actual data packet. So we have the ICMP message coming from 150.1.9.9 going to the multicast group 229.99.99.99, but it's encapsulated inside PIM, and it's a unicast that is going to the rendezvous point's address. Okay, so if we look back at the topology, what's happening here is that there's a unicast message going from 9 to 2, and it's telling 2 about the S comma G entry. Okay, this is the reason that other devices in the transit path, for example, router 3, if we go over to router 3 and we look at the show IPM route 229.99.99.99, router 3 doesn't know about this information, doesn't know about this group, because the unicast message is hopping over router 3 going to the rendezvous point. Okay, so that's the usage of the register message. Okay, the register stop then is going to be the acknowledgement from the rendezvous point going back to the sender, to the designated router, telling it, yes, I now agree that there is that particular source, 150.1.9.9, for this particular group, 229.99.99.99. Okay, so the point of this being is that if the PIM network is properly built, we should be able to go to anywhere in the topology and do just a basic ping, and then look at the rendezvous point, and then the rendezvous point should see the S comma G entry. So for example, if we were to go to router 10, and on router 10 ping 224.10.10.10, then we go to router 8 and look at the show IPM route for 224.10.10.10. Okay, router 8 is the designated router for this particular sender. So the ping message went from 10 to 8. 8 puts it inside PIM and sends it as a PIM register message. So router 8 is going to know about this because it is the designated router. And router 2 should know about this because it is the rendezvous point. So if we show IPM route for 224.10.10.10, we should see the S, G entry that we have the sending address, we have the loopback, and we have the physical interface from router 10. Okay, because when you do a standard ping like this and you don't specify the source, it's going to come from all interfaces that are running PIM. So if we look at the show IPPIM interfaces brief, or just show IPPIM interfaces, we have two interfaces that are running PIM. The ping is going to come from 150.1.10.10 and from 155.1.108.10. Okay, if we want it to come from a specific source, that's when we do the extended ping. So we can say ping, let's say 224, 100, 100, 100. Extended commands, yes. Interface out, loopback 0. Source is going to be 150.1.10.10. Okay, so if we now look at router 8 in show IP mroute for 224, 100, 100, 100, it's not going to know about this because the PIM register message is a unicast that's hopping over the other devices in the topology. But if we look at the rendezvous point in show IP mroute for 224, 100, 100, 100, we should know about the sender. First, we should know about the star, G, but we should also know about the sender and its receiving group. Okay, again, the outgoing interface list is still null, which means that we're not forwarding the traffic anywhere once we receive it. This is because we don't have any receivers that have actually joined the tree. Okay, so this is going to be the next step, is that we're going to signal a receiver. So we have router 10 that's going to be the receiver. And the way that it is going to do this is with an IGMP report message. Okay, an IGMP report or an IGMP join. Okay, this is going to go to the PIM courier on the segment, or the IGMP courier on the segment. And router 8 is going to turn this into a PIM join. So PIM join is going to go up to router 5, and then 5 is going to send it towards router 2. So if we look at the trace route from router 10, trace route to 150.1.2.2, this is the path that the join message is going to follow in order to get to the destination, in order to get to the rendezvous point. So basically, every router along this path should be receiving a PIM join message that has the star, G entry telling us about what is the particular group that we're trying to receive. Okay, so let's go ahead and do a packet capture on, let's say, router 5. So we can see that PIM join message. Okay, so now we're going to go to router 10. We're going to go to global config. We're going to go to interface loopback 0, and we're going to say IP IGMP join 224.10.10.10. Okay, if we look at the show IP mroute for 224.10.10.10, it says the incoming interface is gigabit 0/1.108. The reverse path forwarding neighbor is 155.1.108.8. Okay, so if we look back at the topology, this is on the interface that's pointing towards router 8. Okay, gig 0/1.108. So if we go to router 8 and look at the same thing, so on everybody, let's show IPM route 224.10.10.10. We go to router 8. It says the incoming interface is gig0/1.58, okay, which is pointing towards router 5. So if we go back to router 5 has the star comma G entry, and it says the incoming interface is gig0/1.45. So it means that we're joining in this direction here, okay, towards router 4. On router 4, we're joining towards router 1, okay, out gig0/1.146. So this is our PIM join message. On router 1, we're joining towards router 3. Okay, on gig0/1.13, the reverse path neighbor is 155.1.13.3. So the join is going that way. And then from router 3, the reverse path neighbor is router 2. So we're joining in this direction. Okay, the reason that we're going this roundabout way has to do with the underlay unicast routing. So when we look at from router 5's point of view, and we look at the show IP route to 150.1.2.2, we're using router 4's directly connected interface on gig0/1.45 in order to reach this destination, as opposed to the DMVPN tunnel that's going directly to router 2. Okay, this has to do with the IGP metrics. So if we were to look at the show IPE entropy topology for 150.1.2.2/32, we see that we have the route coming in the tunnel interface with a metric of 25 million. And then we're learning it from router 4 with a metric of 131,000. Okay, so what I'm going to do here is I'm going to modify the tunnel interface. We do show interface tunnel 0. The problem is the bandwidth is artificially low and the delay is artificially high. So I'm going to say the delay is just 1 and the bandwidth in kilobits is the maximum. So if we show IP route 150.1.2.2, we're now going directly to router 2 out the tunnel interface. Okay, what this affects is the multicast routing table. If we now look at the show IPM route for 224.10.10.10, we should now see the incoming interface as the tunnel and the reverse path neighbor is router 2. So in other words, whatever direction that the unicast routing is forward routing is the opposite of the multicast flow. So the outbound unicast interface is going to be the inbound multicast interface. Okay, so let's go ahead and look at our packet capture now. And let's look for PIM, and we're looking for PIM join messages. Okay, so we have PIM join prune that came in from router 10, 155.1.108.10 going to 224.0013. And if we look inside the payload, what this should tell us is the specific group that we're trying to join. Okay, so it says the upstream neighbor 155.1.108.8, tell them that we want to receive traffic for the group 224.10.10.10. Okay, it then goes up to router 8. Router 8 says, tell the upstream neighbor router 5, and we're using 150.1.2.2 as the rendezvous point. Okay, this is another reason why everyone along the transit path needs to agree on the rendezvous point's address, because the RP address is encoded inside the PIM join as we're going up the RPF tree to reach the rendezvous point. So if someone in the middle either doesn't know about the rendezvous point or it has a different rendezvous point address, then we're not going to be able to process the *G join properly. Okay, so let's look at this again from router 10. And now that we've modified our IGP metrics, we should send the IGMP message to router 8. 8 is going to send the PIM message to 5. 5 is going to send the PIM message to router 2. So let's go to router 10. Let's go to loopback 0, and we'll say IP IGMP join 224.11.11.11. If we show IP mroute for 224.11.11.11, it says our reverse path forwarding neighbor is 155.1.108.8, which is router 8's interface here. Okay, so we sent the join message up to router 8. On router 8, if we show IP mroute for 224.11.11.11, it says the reverse path neighbor is router 5. Okay, so next we're going over to router 5. Show IP mroute for 224.11.11.11. Next, it says the reverse path neighbor is router 2. Okay, so we're going to router 2. Show IP mroute 224.11.11.11. And it says the reverse path neighbor is 0 because myself is the rendezvous point. Okay, the rendezvous point is the highest reference point in the tree for the *G. The *G is rooted at the rendezvous point. Okay, so what this is telling us here is that if we were to receive traffic from a sender that's sending to 224.11.11.11, we would forward their traffic out the tunnel interface. But right now, the incoming interface is null. This is because no one is actually sending to this particular multicast group. Okay, so let's go over to router 9, and we're now going to send traffic to this particular group. So we're going to do an extended ping, 224.11.11.11. Repeat count, we'll say 1,000 packets. Extended commands, yes. Interface is loopback 0. And the source is 150.1.9.9, which is the loopback interface. Okay, the first thing that we should see happen is that it checks who is the rendezvous point. Okay, rendezvous point is 150.1.2.2 for this multicast group 224.11.11.11. So we're going to register with the rendezvous point. We're going to tell them we have a sender 150.1.9.9 that's sending to 224.11.11.11. Okay, if the rendezvous point accepts this, we should see the register stop message come back in from the rendezvous point, which is the acknowledgement. Okay, we received register stop on gig 0/1.79 from 150.1.2.2. Okay, so router 2 accepted the registration, and we're now clearing the register flag. So we're saying we can now forward the traffic to the rendezvous point because we received a join message that is actually building the tree. Okay, we received join prune from router 7 for this S, G entry. Okay, the S bit is set, which is the shortest path tree bit set, which means that the data plane might not actually be going through the rendezvous point. It depends on what our forward route is towards the receiver. Okay, so from router 7's point of view, if we do a trace route to 150.1.10.10, notice that we're not going over the DMVPN tunnel. We're going kind of a roundabout. We're going kind of a roundabout manner. We're going from 7 to 6 to 4 to 5 to 8 and then to 10. Okay, so what this means is that when the receiver gets the traffic in from the rendezvous point, so we're going to go to the rendezvous point first, and then the rendezvous point is going to forward towards the receiver is going to leave the shared tree and it's going to join the shortest path tree. Okay, so from its point of view, the shortest path tree to router 9 is going to be a different path. So from router 10, if we do a trace route to 150.1.9.9, the shortest path tree is going through router 3. Okay, so we're going 8, 5, 3, 7, 9. So 8 to 5 to 3 to 7 to 9. Okay, so what this means now is that if we go to the rendezvous point and look at the show IPM route for 224.11.11.11, the outgoing interface list shows the tunnel interface, but we're not the one who's actually forwarding the traffic. Okay, if we go to router 3 and show IPM route for 224.11.11.11, we see this is going to be the one who is the actual forwarder. Okay, and the T bit being set means that this is the shortest path tree going through router 3. So the point being here is the rendezvous point is only used temporarily in the data plane in order for us to connect the sender and the receiver. Once we connect the sender and the receiver, then we're going to follow the shortest path tree between the sender and the receiver. Okay, so let's look at a more obvious example of this. Where router 9 is the sender and router 4 is going to be the receiver. Okay, so from router 9, let's do a trace route to 150.1.4.4. And to get to router 4, we're going from 9 to 7 to 6 to 4. 9 to 7 to 6 to 4. Okay, so this is the shortest path tree, where if we look at from router 4 and do the same thing, trace route to 150.1.9.9, we're going to 6 to 7 to 9. Okay, but if we trace route to router 2, who is the rendezvous point, we have to go to router 5 and then to router 2. Okay, so the shared tree is going to go this way. But the shortest path tree is going to follow that red line. Okay, then we would go to router 2. And router 2, we would trace back to the source. So trace to 150.1.9.9 to 3 to 7 to 9. Okay, to 3 to 7 to 9. Okay, so this shared tree is also sometimes called the rendezvous point tree, the RPT, where the red line, the shortest path tree, is going to be where we have the actual data flowing. But temporarily, we're going to have the packets going through the rendezvous point in order for us to connect the sender and the receiver. Okay, so to demonstrate this, let's go to router 4, and let's go to its loopback interface and say IPm Join 224.444. Show IPM route for 224.444. Okay, it says the incoming interface is gig 0/1.45. The reverse path neighbor is router 5. So gig 0/1.45, which is the blue line that's going over to router 5. Okay, let's look at this on everybody. So on router 5, it says the reverse path neighbor is 155.1.0.2, which is over the tunnel interface. Okay, so the shared tree is going this way over to router 2. Okay, on router 2, it says the incoming interface is null because it's the top of the tree. It is the root of the shared tree. Okay, and right now we don't have any senders, so we don't have an S, G entry. Okay, so next thing we're going to do is we're going to ping from router 9. Let's ping extended to 224.444. Okay, and actually before we do this, let's look at router 6. Show IPM route 224.444. The group is not found. So right now, the only people that know about 224.444 are the receiver, router 5, and router 2. Okay, if we look at router 3 likewise does not know about that group, nor does router 7. Okay, so we've only joined from the receiver up to the rendezvous point. Okay, now we're going to ping from router 9 to 224.444. Let's send 1,000 packets. Extended commands, yes. Interface out loopback 0. Source address 150.1.9.9, which is its loopback interface. Okay, so the tree is now connected. We see we're getting responses back in from router 4. And we now look at the show IPM route 224.444. Router 3 should now know about this because it was in the shortest path tree from the rendezvous point back to the sender. Okay, it said to go to router 7 in order to receive the traffic. But notice the outgoing interface list is null. Okay, the reason why is that this portion of the tree has been pruned because it's not the shortest path tree. So we would have to look at the debugs. Only temporarily does router 3 actually receive the data plane message of the ping going through router 3 to get to the rendezvous point, because once it goes down the shared tree to the receiver, then the receiver switches over to the shortest path tree. Okay, so if we look at router 6 should be the one who's actually forwarding the packets, where the incoming interface is gig 0/1.67, so the red line coming in from router 7, and the outgoing interface is gig 0/1.146 going over to router 4. Okay, from router 4's point of view, likewise, the incoming interface would have changed from gig 0/1.45 to where the shortest path tree is being built. So notice for the star comma G, which is the rendezvous points tree or the shared tree, the incoming interface is gig 0/1.45 because this is the way that we're going to reach router 2, okay, the rendezvous point. So we trace 150.122. We're going out that interface 45. But if we trace back to the sender, 150.199, we're going out towards router 6, 146.6. That's why it's the reverse path neighbor for the actual feed. Okay, so the point being here is that the shared tree is rooted at the rendezvous point, and the shortest path tree is rooted at the sender. And this is going to be an automatic process as soon as you receive traffic in from the shared tree that you switch over to the shortest path tree. Okay, technically you can control this as well. There's a command that is IPPIM SPT threshold. So do you want to, if you say infinity, it never switches over to the source tree, it always stays on the shortest path tree. Where IPPIM SPT threshold 0 says always switch over to the source tree. Okay, which is the default. That as soon as you receive one packet in, that we switch over to the shortest path tree. Okay, questions on what we talked about here today? Okay, there's a question, what's the need to enable PIM sparse mode on the loopback interface? Are we always not going to do the RPF check on those interfaces? You technically don't need PIM on every single loopback interface, but you do need it on the rendezvous point if you're using the loopback as the rendezvous point address. And from any device that you're doing a join or you're doing a ping from, the loopback interfaces you need to enable PIM on. So the simplest solution is that you just enable PIM on every interface, including all of the loopbacks, and then you would never run into a reverse path forwarding check problem. Okay, there's a question, router 2 is the rendezvous point and it's the single point of failure. Is there redundant RP similar to leaf and spine network where two spine routers would be behaving as redundant rendezvous points? Yeah, so in this case, router 2 is a single point of failure. Normally you would want multiple rendezvous points and then you would run Anycast RP between the two of them. Because if router 2 goes down, we're not able to build additional shared trees. Okay, so in that case, like we would choose router 1 as an alternate rendezvous point and then advertise a duplicate address like 1111 on both of the rendezvous points. And then we would configure these two as MSDP peers of each other. And this design is called Anycast RP. Okay, there's a question, can we reduce the multicast tree and use bidirectional PIM? You could use bidirectional PIM. In the case of bidirectional PIM, there's no shortest path trees. There's only shared trees. So in that case, you never switch over to the shortest path tree. You always follow the shared tree through the rendezvous point. So in bidirectional PIM, the traffic is going to go through the rendezvous point always, as opposed to switching over to the shortest path tree. Okay, there's a question, Brian, once multicast is enabled, how do you ensure or configure QoS for multicast traffic? Let's say multicast video for IP cameras in some locations within our network looks blurry, and you ask the network admin to take a look. Normally what you would do is you would create a QoS policy that's based on the UDP ports, and then you would put that into the priority queue. So you could match on the multicast group, but it's probably simpler just to match on the UDP traffic that the camera is using, the UDP ports, and then put that into the priority queue. And then it's going to be treated like any other traffic in the QoS policy. Okay, there's a question, does the router discard the BSR message when the source address of the BSR is not in the unicast table? Yes, it does. So there is a reverse path forwarding check that's done against the bootstrap router messages. So this is another reason why you need to have your underlay unicast routing. Okay, so we said the first step was underlay unicast routing, which in this case we used EIGRP. And we advertised both the transit interfaces and the loopback interfaces because we were using the loopback interface as the rendezvous point address. Okay, but if you don't advertise the loopback interface into IGP and then you use that as the rendezvous point address, then you won't be able to build the multicast trees. Okay, there's a question, if there are multiple senders for the same group, does the receiver send multiple star comma G entries? So the receiver is only going to send one star comma G join. If there are multiple senders that are sending to the same group, then it's going to receive multiple traffic feeds. Okay, there's a question, does the Anycast RP design mean that we can use both of them like load balancing, or are they acting as main and backup? It's active. So you can use both of the rendezvous points, and then they tell each other with MSDP who the senders are. So we have a couple more minutes. Let me go ahead and show that design real quick here. So on router 2, right now, if we show run include PIM, we're using loopback 0 as the RP candidate. So I'm going to say no IPPIM RP candidate loopback 0. And we're going to create loopback 1 IP address 1111. And we're going to advertise this into EIGRP. Network 1111. Okay, we'll then say IPPIM RP candidate is loopback 1. Okay, and you can see I forgot to put PIM on the interface. It's giving me a warning message that it's not going to be functional. So IPPIM sparse on the loopback interface. Okay, so on router 1, we're going to do the same thing. Interface loopback 1, IP PIM sparse, IP address 1111. Under EDGRP, network 1111. Okay, we're then going to configure IP MSDP peers between router 1 and router 2 using their globally routable loopbacks. So we have loopback 0 that is unique, and then we have loopback 1 which is overlapping. IP MSDP peer 151.11 connect source loopback 0. Okay, so router 1 is going to be a BSR, and it's going to be the RP candidate as well. So if we look at on all of the routers and show IP PIM RP mapping, we should see 1111 as the rendezvous point address. Show IP PIM RP mapping 1111. Okay, so if we go back to the topology, let's say that we ping from somewhere close to router 1 from router 4. Let's ping to 224.44.44.44. Router 1 should have learned this. Show IP mroute 224.44.44.44. Okay, we know about the sources. And if we go to the other rendezvous point and show IP MSDP source active cache, this rendezvous point also knows about those senders. So basically they synchronize the register messages through what we call the source active message. So now if someone wants to join the tree, we know that we have these particular senders that are sending to this particular group. So it effectively allows you to do active-active forwarding. Okay, we have time for about 2 more questions. There's a question, once the shortest path tree is built, will the failure of the RP affect the ongoing multicast traffic? No, it will not. Okay, so as long as the shortest path tree is not routing through the rendezvous point, technically the RP address could go down and you would still be fine for forwarding your multicast traffic. It would only affect new trees that you're trying to build, new register messages and new join messages that are going to the rendezvous point. Okay, there's a question, is it not possible to achieve active standby RP redundancy with any cast just by announcing the same RP address with different masks and avoiding using MSDP at all? Yes, you can. And that feature is called Phantom RP. Okay, normally you use this with bidirectional PIM. But with Phantom RP, you have one loopback that is a longer mask than the other one. So they have duplicate addresses, 192.168.3.1, 192.168.3.1, but one of them has a mask of 255, 255, 255, 252, and the other one is a 248. So this is the primary rendezvous point, and this is the backup rendezvous point. The difference, though, is that it's not active-active, it's active standby. Okay, so otherwise that's going to do it for today's session. I hope you guys enjoyed IP multicast routing, and I hope that you can attend the rest of the sessions that we have going on this week. Again, if you take a look at INE.com and then under Networking Week, tomorrow we have Understanding Spanning Tree and Getting Started with ASA Firewalls. Wednesday, we have IP addressing and subnetting. Thursday, we have OSPF stub areas. And then Friday, we have the Q&A session. Okay, also make sure to register for the one-on-one study session where you could win a study session with one of our instructors for a topic of your choice. So thanks everybody for attending. And I hope to see you back here for further webinars in the future.